some really amazing talks and discussion. And the ideas I'm going to lay out today were kind of inspired by the conference, along with lots of other things that I've been thinking about over the last couple of years. So I first kind of start by thinking about what neuroscientists mean when they use the term representation. And neuroscientists use this term in sort of a willy-nilly way. They don't really think twice about calling something a representation. And if the kind of the most obvious, well, I guess what neuroscientists mean by representation is really some kind of systematic relationship between features in the world and activity of neurons in the brain. And the most obvious versions of this are the kind of topographically organized primary sensory cortices, right? So you're probably all familiar with the sort of somatomotor homunculus or somatosensory homunculus. And you may also be familiar with the retinotopic, organized visual cortices. We also have, tonotopically organized auditory cortices. So the primary sensory cortices are generally organized in a way that's kind of systematically, topographically related to some feature out in the world. Now, we also know that there are examples of things that neuroscientists call representation, where the macroscopic organization of the brain doesn't necessarily map onto the outside world. So the best example of these is from what's now come to be called the zoo of hippocampal cells. There's, or sort of medial temporal lobe cells. So there's a bunch of different cells, types of cells in the medial temporal lobe that quote unquote represent. I'm going to stop using the scare quotes, but whenever I'm talking about neurorepresentation, you could assume I'm using the scare quotes. These represent things out in the world. The most famous are the place cells, right? Where an individual place cell responds to whenever the animal is in a particular place in space, right? And the reason that I say that they're not macroscopically spatial isomorphic is that nearby place cells in the hippocampus don't necessarily respond to nearby places in space, even though they respond systematically to a place in space. We also see these other things like head direction cells, grid cells, border cells. In each case, they respond systematically to a thing out in the world, but nearby cells don't respond to nearby things in the world. Nonetheless, we're happy to call them representations. And so one way to think about, what neuroscientists mean by representation is in the context of what we call a receptive field, right? What are the things that cause the neuron to fire? So, the earliest idea of receptive field came from, for example, the early work of Hubel and Wiesel, who showed that, different places in the visual field of a cat cause different neurons to fire, right? And then that gets more complex in terms of neurons having, receptive fields that reflect motion in a particular direction, or things of a particular size. But you can use that, you can kind of push that logic forward to think about any particular neuron having a quote unquote receptive field that basically is defined by the class of things that cause that neuron to fire. So let's take this image of Cinque Terre, right? What if I see a neuron in the brain that fires in relation to this particular image? What would we say that neuron is representing, right? And there's basically an infinite set of things that it might be representing, right? It might be representing blue things. It might be representing spatial depth. It might be representing memory for a trip to Italy. It might be representing fear of heights, right? Just based on this one particular finding of neuronal response to an image, we can't really say, right? There's an indeterminacy of what's being represented here, and this actually, there's a I think a deep parallel here with the kind of indeterminacy that's been talked about in the philosophical literature regarding representation. But the point is that as scientists, we kind of try to address that indeterminacy with experiments, right? Where we basically say, well, let's try a bunch of things and see what causes it to fire and what doesn't, right? And this often goes under the term of selectivity, right? We want to figure out basically what are the sets of things that this neuron is selective for, the things that cause it to fire in relation to all the other things that don't cause it to fire. So Here's an example from the human neuroscience literature around the what's come to be known as the fusiform face area, right? So early work by Nancy Canwisher and colleagues showed basically that this region in the fusiform gyrus is more active for faces than for many other different types of stimuli, scrambled faces, houses, hands, various objects, and so on. And so the claim that came out of that early work was that this area represents faces, and it is kind of a ultimately the claim is sort of a module for face processing, such that that's what it does. Um, but that ascription is only as good as the class of things it's been tested against, right? And so later work by Isabelle Gauthier came along and said, well, humans are experts at face processing. So what if you look at people who are experts in the processing of other types of objects? So they looked at people who are bird experts or car experts and basically showed that, well, the car experts show activity in that same area for cars, but not for birds. The bird experts show activity in that same area for birds, but not for cars. And so they tried to ascribe a function that is really more about kind of flexible processing of expert categories at a subordinate level. So the point here is that these representational ascriptions are really only as specific as the set of possibilities that have been tested. Now, in more recent years, neuroscientists had moved beyond kind of thinking about individual classes and have started thinking about representation, what we call representational spaces, which is you can think of as sort of like the organization of neural responses across a larger range of content or a larger range of potential representational features. So this is probably the most famous example of this is from the early work of Nico Kriegescourt, where they took data from both monkeys and humans, looking at a large range of different types of objects, animate objects, inanimate objects, human, non-human, natural, artificial, and so on, and basically looked at the similarities. So you record activity either from a bunch of individual neurons in the monkey inferior temporal cortex or from a bunch of voxels using fMRI in the human inferior temporal cortex, and basically ask how, in this case, it's how dissimilar are the patterns of activity across those neurons for each of these different categories of objects, for each of these different individual objects. And what they see is that indeed the same class of objects shows much more similar patterns of activity. In this case, you see this sort of blue area. So blue here means not very dissimilar, so highly similar. So you can see that, for example, the faces are all responded to very similarly across these neurons, both in monkeys and in humans, right? So this shows you a couple things, right? One, it shows you there's this higher level structure such that, similar types of objects are responded to similarly within this brain area. And this seems to survive across both monkey and human cortices, right? And so it tells us that there's a similar, that we think that these animals are representing this content similarly. That's the claim that comes out of this type of work. Okay, so what I want to do now is turn to, how representation, the concept of representation is increasingly being thought of in computer science. And there's a very old classic way of thinking about representation in terms of, say, for example, moving between a binary versus a decimal representation of a number. That's kind of a lossless transformation that is not what I'm talking about here today. What I'm going to be focusing on is a concept of representation that's really come about in the last 20 years through a set of people who now really are, we think of as doing what we call deep learning. But interestingly, this work really came out of a set of people who called what they were doing representation learning, right? And so this, one of the main deep learning conferences is the International Conference on Learning Representations, where they explicitly say representation learning is now what's really referred to as deep learning. So why is that? Well, let's imagine what happens when you want to perform a task on some data, right? So let's say that this is my cat Coco wearing a hat. Cats don't wear hats usually, but we had her wear a hat one day. Um, and you know, the when I see that image, I think, hey, that's Coco in a hat, right? Um, but you know, there's lots of different. When I do that, I'm transforming that image from a bunch of intensity values hitting my retina to a proposition, Coco in a hat, right? And if we wanted to build a model like a deep learning model to do that, the idea is that the image needs to be transformed in service of the task, right? And there's many different tasks one can imagine doing with an image, right? You might imagine you just want to find the edges or compute the average brightness. But in this case, what we want to do is say, what's the object that's in the photo? What's the class of the object, right? In this case, I want to say, what's the particular instance, which is Coco. But if I'm training a deep learning system to recognize objects, I probably want it to recognize, hey, this is a cat. So the goal of representation learning is basically to transform that image into some kind of other format that can support performance on a particular task. And so how does that work? And how does, in particular, why do we think of deep learning as being somehow different from sort of classic connectionist models? So many in philosophy will be familiar with, connectionism through all of the debates, in the last century about kind of what connectionist models can and can't do. And, in some ways, the main difference between, the main kind of surface difference between what connectionist models did and what deep learning models do is the depth of the model, right? Whereas in classical connectionist models, you usually might have one hidden layer and input and output layers, whereas in deep learning models, you can have tens of hidden layers, and that the ability to you know to learn those deep layers has come about through both kind of algorithmic improvements and kind of computational hardware improvements, as well as through the availability of lots of data. But the fundamental difference, the real thing that has changed the game for why it is that deep learning is so effective is the fact that deep learning networks actually learn their representations, as opposed to the examples from classic connectionist models where usually the representations were sort of handcrafted and built in by the modeler. So in deep learning, the modeler provides, whereas in classical connectionism, the modeler provided the representations. In deep learning, the modeler provides, one, the architecture. So for example, it says, well, this architecture is going to be one that involves convolutions, right? And it's going to be a particular depth, and it's going to have particular types of layers. Provides a learning rule, right? So it's going to learn, for example, through backpropagation. And it provides a task, right? Which basically is defined in terms of the loss function that the model is trained to reduce, right? In this case, it might be mapping from particular letters to particular visual inputs out to a categorical decision about letters. So as I mentioned, deep learning has really become amazingly effective at a set of tasks like object recognition in the last few years. So I fed this image of Coco into VGG19, which was a state-of-the-art deep learning system from 2014, and it gives you back the probability of like what's being seen in this image. And the most common, the most highly probable thing it told me was Siamese cat. Obviously, Coco is not a Siamese cat, but she's a cat with a 0.18 probability. It also said with 0.1 probability that there's a bath towel in the image, presumably kind of going off of the fact that the hat has kind of a towel-like texture. Fast forward 5 years, I plugged it into Clarify, which was state of the art as of about last year, and it says with 99.5% likelihood that there's a cat in the photo, even though Clarify was almost certain never trained on any pictures of cats wearing hats, right? And this fits with what we've seen in the ImageNet visual recognition challenges, where even as of 5 years ago, VGG19 was probably about at human level at least on the ImageNet challenge, and now we've seen that networks in the last 5 years have become sort of much better than human level at performing this one particular task, right? Which is basically saying, what's the class of object? What's the kind of relatively basic level class of object that you're seeing in this image? Now, what are these networks learning, right? So neuroscientists have spent a lot of time trying to dig in to say what's being represented in the brain of animals. And it turns out that you can do this kind of like what you might think of as in silico electrophysiology with neural networks as well, where you basically say, for example, this is work by Chris Olah, really amazing work you can find at his website here, where you can basically say for any particular patch in the image, let's find the units in the network at some particular level that are kind of most strongly engaged by this particular part of the image. And then we can ask, basically using some tricks, we can basically say, what's the image? Find the image that would most strongly activate this particular unit, right? And this is an example of, for two units in this picture, one that kind of, is most strongly activated by the dog's nose. And you see that when you sort of synthesize the images that maximally activate that unit, you see they kind of look dog facey, right? They're not perfect dog faces, but they look a little bit dog facey. Similarly, if you take the unit that activates most strongly to its leg and say, what are the images? Find the images that maximally activate this unit. They look kind of leggy a little bit, right? Or at least sort of have some texture similar to that. So what this shows is that, we can understand what these deep networks are learning. And, the natural thing to call this is a representation, right? That basically there's some structure that is being identified by these particular units that because these are units that are relatively high up in the network, it's relatively high level structure. If you looked at the units that were much earlier, they would be in the network, they would be sensitive to things like edges and much simpler features. So what do these have to do with brains? Well, the one thing that I'm going to focus particularly on a set of networks that are referred to as hierarchical convolutional neural networks. And these are networks that have been particularly effective at these object recognition problems. And so this is a figure from my colleague Dan Yeamans, who with Jim DiCarlo has done a bunch of work trying to understand how the representations and the function of these neural networks relates to the function of the primate visual cortex. So on the bottom, you see the structure of one of these networks. And in particular, what you see is that, you start with networks that are really looking at kind of pixel level information. And then those, through a set of operations, get distilled over time into kind of higher order representation. So what Dan's work has done is basically said, if you take a network that's been trained on a particular set of images to do the object recognition problem, a behaviorally optimized network, and then you take an animal and have it view the same images, you can then basically use the neural network, use the signal from the neural network to predict patterns of activity of neurons in the primate brain, even though the network doesn't know anything about the primate brain. All the network knows is how to do the object recognition task. And what you see is that successively higher levels in the neural network can predict very well patterns of activity of neurons in successively higher layers of the primate visual cortex. So this work and lots of work like it by others, like Nico Kriegescourt, has really established this kind of isomorphism between the function, the patterns of activity and the quote unquote representations that are being developed by these these artificial neural network models, and those that we actually see in the primate visual system. And in fact, you can see that these networks do much better at predicting. So the y-axis here is basically the amount of explained variance in the neural data, right? And basically, what you can see is that the better the network does at performing the object recognition problem, the better it also does at predicting variance in neurons. And in fact, I mean, this is some cool work from Ecker's group and Andreas Tolles. Basically, you can show that a network that was only trained to do object recognition can basically fit neural data just as well and predict neural data just as well as a network that was actually trained to predict neural data. And so basically, you don't even need to know anything about what neurons are doing. All you need to know is how a convolutional neural network solves the image recognition problem. That allows you to predict the activity of neurons in the brain, in this case in V1, just as well as you could using a model that's purposely trained to predict neural activity. You can even take this one step farther and start to do the kind of thing that Chris Olah does, with his neural network. So this is some really amazing work by Jim DeCarlo's group, Puya Bashavan, where they basically have a monkey looking at images, and then they use a neural network to basically predict what would the images be that would cause this particular neuron to activate most strongly. And what they can do is basically come up with these things you see on the right, these sort of synthetic, what they call controller images, that basically cause individual neurons to fire more strongly than any of the many naturalistic images or sort of other complex types of images that they show. So basically, they can sort of find the perfect image, or at least the most perfect that they know image for each of these neurons, right? Again, using that model. So this is telling you there's something really fundamental that's related between the neural network models and what primate brains are doing. Okay, so I want to lay out a way to think about like what these models are actually doing, which is sort of requires us to think of learning as like function approximation. So the idea is like, when I see this particular image, right? What happens? That image goes into my brain, it goes through my visual cortex, and it comes out with me saying, hey, Coco in a hat, chuckle. What a neural network is really trying to do is basically somehow approximate that very complex function, right? The mathematical function that goes from this retinal input to this statement, basically approximating that function using some kind of parameterization. Now that this is challenging, right? If you take that image, right, and so this particular image is a grayscale image. It's about 1.5 million pixels. So each voxel, each pixel in that image has 256 possible gray values. So that's a 256 to the 1.5 millionth is a big number. And so that's the number of possible images, even out of this very small, retinal, or this very small input. So a fundamental question is, how can a system like a deep network, which might have tens of millions of parameters, learn to classify images in this very high dimensional space? And in particular, there's a problem that arises when we think about how would we go about learning the relationship between, any possible one of these 256 to the 1.5 million images and some, category. And the problem is something that in computer science is referred to and mathematics is referred to as the curse of dimensionality. So the idea is that the number of samples that we need to span a space of features grows exponentially with the number of features. So let's think about this. If we just have a single pixel and we want to kind of fully sample the space of possible inputs for that single pixel, we need, in principle, 256 different samples to get a full sampling of that space. For two pixels, now we need 256 by 256 samples in order to see every possible value for those 2 pixels. And that goes up exponentially, right? So let's think about how one might go about learning, to map those images onto categories, right? So the simple thing you might imagine doing is basically just like taking a specific image, right? The particular pixel values in an image, and mapping those onto a category label. So for this particular image, the label would be cat. Let's just stick with the basic level categories, right? This is what we call a model-free learner. It doesn't know anything about the world other than just remembering kind of which particular inputs go with which particular outputs, in this case, which category. The problem is that you could never obtain enough experience to learn the labels of all the possible images for even for that small 1400 by 1000 image space. So for that particular image, if given the 256 by 1.5 million possible images, if you learned them 1 nanosecond per image, it would take or still take orders of magnitude longer than the time elapsed since the Big Bang to see and remember all of the possible combinations between of images and labels. That's not how we do it. I mean, there are some ideas that, some types of learning actually probably do occur in a model-free way, but clearly our learning of category labels for images is not occurring in a model-free way. And what this highlights is the fact that, we need a model in order to behave adaptively in the world. And one way to think about what that model is doing is providing us with some inductive biases, right? It's basically allowing us to project the very high dimensional data from the world into a lower dimensional space. And what this does is allows us to generalize. So basically we're saying all those dimensions that we kind of collapsed over, they don't matter, right? We're going to generalize across those. In the case of, my image of Coco, the fact that like this is a black and white photo, this is a color photo, those, we're going to generalize over those for the purpose of kind of, recognizing objects, at least in this case. But importantly, that generalization is only going to be successful if it accurately reflects the structure that generates the inputs, which in this case is, the physics of the world, and presumably, the physics of our eye and a few other things. So I'm going to make the argument that, in some ways, these projections are representations, right? And I'll finally get to the argument that these are basically necessary for any organism to behave in a adaptive way in an environment. So there's a really interesting paper that came out a few years ago by Henry Lin and colleagues that sort of laid out one argument that's been really influential in my thinking about this, for basically addressing exactly the question I raised. Is how is it, they say, why does deep and cheap learning work so well? By cheap, they mean relatively small numbers of parameters compared to the exponential number of possible inputs. And the argument is in the particular case of these convolutional neural networks for visual object recognition, that the structure of those networks encodes an inductive bias, right? That the fact that they say basically, each unit is going to look at a small patch in the previous layer, and then those are going to sort of combine compositionally across layers, that particular architecture encodes an inductive bias that matches the generative structure of natural images, and which arise ultimately from the physics of the universe, right? That it turns out that things are relatively low dimensional, right? That effects physics are relatively local, right? That things are relatively symmetric, right? The fact that symmetric with regard to various transformations. So for example, if I rotate that picture of Coco 3 degrees, it's still Coco, right? And hierarchical, the fact that things in the world are generated through a set of hierarchical physical mechanisms, and that hierarchy, the fact that edges ultimately come together to make objects, all of that is represented in the architecture of those networks. And in particular, the compositional nature of the networks, the fact that you take you summarize one network, and then that summary basically gets used at the next layer, that compositional nature allows the number of necessary parameters to grow linearly rather than exponentially with the complexity of the input. So one question that can get raised, that Rosa Cow raised when I presented this stuff at Stanford, is, but there's no natural dimensionality, right? How do you know what the right dimensionality is? And that's exactly right. There is no natural dimensionality. But the argument that I want to make is that any organism that's going to behave in our world with the physics that our world has is going to have to address the curse of dimensionality. So, humans have millions of photoreceptors, but even a fruit fly has on the order of 5,600 photoreceptors. So even if each of those is just encoding a binary signal, 2 to the 5600th is still a pretty large number, right? And fruit flies are probably not going to be able to kind of go through the world and record all of those possible experiences and inputs on their retina. So I think that the argument here is that in a complex world like the one that's generated by the physics that we have, any possible dimensionality for adaptive behavior is going to require dealing with the curse of dimensionality, and thus is going to require some kind of model-based system that encodes inductive biases. Now, those representations don't have to come through evolution, right? We think that some of them are encoded in the architecture of the mammalian visual system. Others get encoded through experience via mechanisms of plasticity. So many of you may be familiar with this work by Colin Blakemore, where he raised cats in environments where they could either only see horizontal lines or only see vertical lines. And basically what you see is that when an animal is raised only seeing horizontal lines, they don't develop any neural representations for vertical lines, and vice versa for horizontal experience. So the idea is that there's multiple places where this experience, where these representations can come from. Okay, so to the philosophical question. Obviously there's lots of different ideas from philosophy about what representations are meant to mean, and in particular, what's the criterion for something being a representation or not. I will say up front that my knowledge of this area is relatively limited, but in my reading, I sort of came across a couple of relatively compelling ideas about if we want to decide, are these representations that I'm talking about really kind of bona fide representations? What do we have to do, right? And so, Ramsey lays out this quote unquote job description. One way that that's described is, the question, are there mindless systems like brains or artificial neural networks in which an internal element is performing a role that is most naturally or intuitively or justifiably or beneficially viewed as representational in nature, right? So Nicholas Shea's paper lays out a set of somewhat more kind of explicit criteria that I'm going to follow as I kind of walk through, do we think these are really bona fide representations? So first we have to give an explanation of how the system is operating, how it's doing what it does, and give a representational explanation of that, and then show how that explanation succeeds, and show why, why is it really a representational explanation? But let's do that for object recognition. So first, what's the thing that we're trying to explain? Well, we're trying to explain the fact that, given many different types of inputs, an effectively infinite number of possible inputs, how can we see those and come up very quickly within hundreds of milliseconds with an appropriate label, right? Across many different image manipulations, noise, spatial transformations, color, and so on. What is our representational explanation today? Well, the representational explanation that I want to give here is the one that basically links artificial convolutional neural networks to the primate visual system, basically showing one that, both of these systems, claiming at least that both of these systems perform a hierarchical decomposition of an image, right? Starting with very low level features, hierarchically building up to very high level features. And based on, the results from a lot of work in the last 5 or 6 years, claiming that the way that these two systems work is fundamentally similar, supported by the fact that one can very effectively predict the activity of brains from the activity of these artificial neural networks, in a way that follows the same system, and in a way that it seems very difficult to explain without the concept of representation, right? In the way that I showed, what are the units in the neural network doing, in Chris Ola's work? Well, if we look at the thing that drives those units, it's things that look object-like, right? And so those are certainly most naturally described as representations of particular features in the world. How does this explanation succeed? Well, it allows, these networks now can actually do even better than humans at object recognition, we can, as I mentioned, predict neuronal responses in primate brains, and we can actually use the models to generate stimuli that activate neurons in the brain more strongly than any of the thousands of naturalistic images that have been tested, right? Those all seem like a pretty good success in in explaining, at least in terms of explanation by a prediction, what these particular neural systems or artificial neural networks are doing. Okay, so now the crux, right? Um, what are the kind of properties that the representational properties of the system would have to be for that explanation to succeed? And the first is clearly causal dependency, right? We need it to be the case that the putative representations are reliably triggered by the feature, and electrophysiology shows us that. We can decode images based on the activity of neurons, which wouldn't happen unless those neurons were reliably triggered by the features. Now, obviously, this is necessary but not sufficient to call those representations. It could just be that they're receptors, which is generally taken as diminutive, with respect to representational status. Perhaps more strongly is the idea that of the structural relationships between the content of the representations and the visual world. The idea being that the visual input is being projected onto a low dimensional manifold, right, that reflects the structure of the world, reflects the structure of, in this case, natural images, right? The fact that natural images have particular features such that we can generalize across features that don't matter. And the argument is that it's only through representation, through, I should say, the lens of representation. It's only through the lens of representation that the success of these systems and the fundamental functional isomorphism between the visual and artificial systems makes any sense at all. Finally, we need to show that we can somehow decouple to get away from these just being receptors. Can we decouple the representations from the triggering stimulus? Can they play their representational role in the absence of the triggering stimulus? And I think that recent work in neuroscience has provided really compelling evidence for this. This is work from last year from Carl Dieseroth's group that basically did, what you might think of as inception of visual stimuli. So that basically they train an animal to do a visual task based on particular visual inputs. They record activity across a bunch of neurons, and then they basically, without any visual stimulus, reinstate those patterns of neural activity, and basically show that the animal can perform the task just as well on those artificial neural implants as they can on the visual stimulus itself. I think perhaps an even more compelling version of this comes from some human work, and I think you're probably not going to be able to hear. I don't know if you'll be able to hear the audio from this, but I'm going to play it, and I think it has subtitles anyway, and I'll kind of narrate as it goes. So this is work from Nancy Kanwisher along with a group in Japan, where they basically identified in a human the part of the fusiform gyrus that was sensitive to faces. And this is a person who has electrodes implanted to identify epileptic seizure foci. So they're sitting in the hospital with electrodes placed under their temporal lobe, and one of them happens to be right on top of this area that was face selective. And they basically say, well, what happens when we stimulate that? And I'm going to show you. Oh, do we not get the video? Let's see. Okay, here goes the video. So basically, this person is looking at just sort of a blank screen, and they're about to have their face area stimulated. So they're not seeing anything, and you'll see a little blip down here on the bottom right when it gets stimulated. So he says for the first second after the stimulation started, so he's just looking at sort of like a chalkboard right there, nothing on it. Saw an eye, a mouth. So he saw face-like features. I was looking at a soccer ball, or as you might call it, a football. And again, when he simulated, sees an eye, and a mouth sideways on the ball. Now what happens when he's looking at this person's face when they stimulate him? Your face completely changed. So this seems to be the region that they're stimulating actually seems to be potentially even more specific, right? It seems like it's really specific to eyes and maybe to mouth rather than kind of the entire face. His hair stays the same, doesn't change what he sees in the hair. Do it again. Stimulating again. Face turns into a cartoon character. So clearly this, this stimulation of this area both can drive perception of faces when they don't exist and change the perception of a face when it does exist, showing that it is an area that seems to be essential for face perception. So now he's being shown, you'll see in a moment, a set of kanji characters. And again, he's going to see a face in those characters. So this, okay, so that it's really difficult for me to see how you explain that sort of inception without reference to representations that are triggered by a stimulus. Okay, so I want to make one final comment, right, which is about this tension that's been in the literature, in the philosophical literature, and the cognitive science literature for a while between sort of dynamical systems approaches and representational approaches. And this is, going back to that literature in the light of recent neuroscience work is really interesting because in neuroscience, people are now perfectly comfortable sort of mashing together representational talk and dynamics talk. And from the standpoint of sort of representation as lower dimensional projections, this is perfectly natural. It could either be a dynamic pattern, it could be activity of particular neurons. And in fact, the inception work that I showed you earlier, what they actually did was not, inducing activity just in specific neurons, but actually replaying dynamical patterns of activity in the visual cortex. And this is from the paper, right? Replaying these dynamical patterns, they say, gives you precise control over naturally occurring, widely distributed, and finally resolved temporal parameters and cellular elements of the corresponding neural representation. So there's other examples of this that I talk about in the paper. Neuroscientists are completely comfortable mixing together kind of dynamics talk and representational talk, and I hope that this can kind of provide some degree of potential rapprochement in the philosophical literature as this kind of work becomes more prominent. So just to wrap up, I mean, I hope I've convinced you that there's a really interesting synthesis that's emerging between neuroscience and machine learning that gives us a way to think about what representations do in terms of dimensionality reduction that reflects the statistical structure of the input, reflecting among other things, the physics of the world, along with the tasks that are being performed. And the argument from machine learning theory basically shows us that without these types of representations, without this type of dimensionality reduction, these inductive biases, basically any kind of intelligent behavior is simply impossible. And finally, that current work in neuroscience is really starting to blur the line between representational and dynamical systems approaches. I will stop there, and I look forward to hearing the comments from my colleagues.